Hello everyone, this is group 10, Adarsh, Mohit, Sahu and Praneet, Nandan. Our lecture topic is support vector machines and focusing on kernel. First, we'll start with the general definition of a support vector machine. A support vector machine is a model of supervised learning. It is used as a classifier mainly. What is a classifier? It is used to classify points into two separate regions, two or more. So let's say we have some data which I have plotted here in the graph. We have two axes. For simplicity, I have taken just two. Let's say x1 and x2. These are the two axes. We have data on these axes, and there are two types of data. Some are circles and some are crosses. What we want to do is, based on this data which we have, we want to find a plane such that we can divide these data into two regions. One region has all the crosses, and one region has all the circles. So that when we get a new data, let's say we get a new data here, star. We don't know what star is. Star can be circle or cross. Based on the plane which we have, we'll then predict what this star is more probable to be. Here, since this plane is the one we draw in here, so then we'll predict this is more likely to be a circle. So this is how support vector classifier works. We saw in class that the way we find this plane is we try to minimize a function half of norm of w square on all w, subject to the conditions that yi w transpose xi minus b is greater than equal to 1. So what are these w's and b's? W is basically the slope counterpart of this plane. In this diagram I just have 2 dimensions, but in general we can have n dimensions. So then the divider which will divide the two regions will be an n minus 1 dimensional hyperplane. So there this W will be an n tuple. So then this W transpose Xi will make sense. Xi I goes from 1, 2, 3 up until M. This I is the number of data points we have. So for each data point, and this Yi is the classification. If it's a circle, we say it's +1. If it's a cross, we say it's -1. So using this, we these conditions should be satisfied, and then we try to minimize the norm of w square by 2. Then the w we get is the best equation of the plane, which will divide the two regions such that any testing data that we have will be classified better. So this was the SVM which we did in class. Now, first, I like to move forward to Lagrange duality. So in the case of Lagrange duality, it is something that has been inspired by classical mechanics. Uh, in classical mechanics, we have something called a Lagrangian. What the Lagrange duality does is, I'll first define it in general, and then after that, I'll tell you how it's used in SEM. So assume we have some function fw, and we want to minimize this function with respect to w. You already see that it's somehow similar to the SVM problem, because there also you try to minimize something. And let's say we have a constraint that there is a family of functions giw, which all should be less than equal to 0. Gi is a family, I goes from 1, 2, 3 to m. So you have a family of m functions, and all of them should be less than 0 at w. So this is the problem that we have. We want to minimize fw with respect to w such that this condition is always satisfied. So what we do is we define a generalized Lagrangian, which is defined here in terms of w and alpha. Alpha is something extra that we introduce. What alpha is? Alphas are called uh, Lagrange multipliers. They're basically variables that we introduce on top of the ones we have, so that we can manipulate the problem into something which is easier to solve. So we define the Lagrangian as fw plus sum over I going from 1 to okay. So let's change it. It's the data we have is not 1 to m, it's 1 to k. So sum going from 1 to k, alpha I, gi, w. So first of all, we define a quantity theta p. P here, the subscript p stands for primal. So what theta p is? Theta p, we try to maximize the Lagrangian with respect to alpha, such that alpha I is always greater than 0. This condition is important. What this condition does is, see, if alpha I is, all the alpha i's are greater than 0, then this second quantity, the coefficients of all gi is always positive. Mm, so if we are trying to maximize this in terms of alpha, then this condition which we had, this condition becomes important. If we have a system where this condition is not satisfied, that is we have some, let's say g3 is greater than 0 at some point. So what this maximization will do is that alpha 3 can go to infinity to become maximum. And when alpha 3 goes to infinity, this whole Lagrangian will go to infinity. So the theta p will become infinity. So what happens is, if this condition is not satisfied, then theta p becomes infinity. If this condition is satisfied, on the other hand, then all the alphas are positive, all the gi's are negative. So increasing any alpha decreases the theta p. So what we do, the maximum will occur when all the alphas are zero. So what we'll get is theta p is equal to theta p is equal to fw. So theta p is equal to infinity if any gi does not satisfy this condition, and if all the gi satisfy this condition, then theta p is equal to fw. Then after that, what we do is we just minimize with respect to w theta p, and we get back our original problem, that is fw. So this makes sense if gi's satisfy this condition. If gi don't satisfy this condition, then this goes to infinity. So in case that condition is satisfied, we get fw and we get back the original problem. uh, you can write it in extended form as theta p is equal to minimum over w maximum over alpha, so that all alphas are positive, and the Lagrangian. Now we define another quantity, theta d. Here d is stands for dual. Theta d is a function of alpha, and that is after minimization of the Lagrangian over all w. So in the first case, we were defining a theta p which maximized overall alpha. But here we are defining a theta d which is minimizing over the w. And after minimizing over w, if we maximize over alpha over theta d, we get a maximization over alpha, minimization over w, and the Lagrangian. So we have two quantities here. One is minimization over w. Then first we are maximizing here, then minimizing over w. In this case, we are first minimizing, then maximizing. So this is a well-known result in logic and maths, which is called the min-max result sometimes. Which says that the min-max of a quantity is always greater than or equal to the max min of that quantity. So it have what it basically says is that the min-max that we have here, this, and the max min that we have here, these, it says that the max min is always less than or equal to the min max. So as you remember, the min max was the original problem we had in case it did not diverge to infinity. So we get that this, if we solve this problem, the value we get is less than the original problem in case the conditions are satisfied, which we had. So this min-max result, you can think of it in such a way that if we first minimize over one parameter and after that maximize, we are already at a lower plane. So after minimizing over w, the Lagrangian becomes just a function of alpha. Even after we maximize it, it cannot exceed the original plane we got, because we already minimize over w. So that is always less than or equal to, if we maximize first and then minimize, then there is scope that it can go above the real minimum that is there. So using this, still there is a less than equal to sign. This less than equal to sign becomes an exactly equal to sign when a certain conditions are satisfied. These certain conditions are called the Karush-Kuhn-Tucker conditions, the KKT conditions in short, which says that, let's say there exists some omega star and alpha star Omega and alpha are the two parameters of the Lagrangian. There exists some omega star and alpha star such that the differential over all omega I of the Lagrangian at these points is equal to 0. Alpha star gi omega w star is equal to 0, and alpha star is always greater than equal to 1. So these three conditions, along with the condition that we had in the starting, that is gi should be less than equal to 1. So if gi is less than equal to 1, gi star is obviously less than equal to 1. So this extra condition that gi omega star is less than equal to 1, sorry, not less than equal to 1, it's less than equal to 0. So gi less than equal to 0. So these conditions together, they are called the KKT conditions. And if these are satisfied, then this omega star and alpha star will give like um, this min max condition. Let's say this one was the primal problem. So let's say this gives P star at W star and alpha star. This gives D star at W star and alpha star. So if these KKT conditions are satisfied, instead of less than equal to, they are exactly equal to. So instead of solving the primal problem, that is minimizing FW over omega, we can solve the dual problem, which is maximizing over all alpha, alpha I greater than 0, and the minimum value of the Lagrangian based on the W. So we can solve this instead of solving for the minimum of W, and we'll get the same result. So this is how we change a problem from primal to dual in this particular case using Lagrange multipliers. And why we are doing that, that will become apparent later on. So now we move back to the SVM. In SVM, our problem was minimizing over W, half of the norm of W square, such that these conditions are satisfied. So first of all, we define a function gi. What is gi? Gi is just minus of yi wt xi plus b plus 1. So why we are doing that? Because this condition which we have, this has to be greater than equal to 1. So if we take 1 to this side, we'll have yi wt xi plus b minus 1 is greater than equal to 0. And then we multiply the whole by minus 1. So we'll get this is less than equal to 0. So we get giw less than equal to 0, which was the condition we took while we were solving the dual problem. So this then matches to that condition, and here we can define f w as half of w square. So again, we get to the same condition. We have an fw which we want to minimize with respect to w, and we have a family gi w which are less than equal to 1. And the number of such equations which we have is I from 1 to 3 to m. So basically, we have as many equations as the number of points that we have. So again, we define the Lagrangian, which will have parameters w, b, and alpha. The Lagrangian is f. Basically, this is the f. These are the Lagrange multipliers, and this is the g, which we just now wrote down. So we need to. The primal problem was finding the minimum over fw. So the dual problem will be finding the first we find the minimum over w of the Lagrangian, and then after that we maximize over alpha such that all alpha is a greater than 0. So one thing to note here is minimizing over W does not mean only minimizing over the slope part. You also have to take the constant part, because that is also a parameter of the that is also a part of the problem that we have. That is not Lagrange multiplier that we introduce later on. That is there already. So minimizing over Lagrangian will imply minimizing over W and B both. So this we do now. So first we take the derivative with respect to w. W is the slope part, like we said before. So we get this equation, w minus sum over 1 to m alpha I ya xi is equal to 0. Solving this, we get w is equal to sum over I to m alpha I ya xi. This is an extremum, and if you check the double derivative, you'll find that this is also the minimum value. This is the value of w at which the Lagrangian takes the minima. then we can replace this back into the equation that we originally had, back into this equation. Instead of w, we'll replace this. So what we get after solving is that the minimum over w, just this is this w, b we have not yet minimized. Minimum over w of the Lagrangian will give me this form, this extended form. After this, if we minimize the Lagrangian over b, we find that sum over I1 to m alpha I yi is equal to 0. This implies that this last term that we had, this is equal to 0 in case of taking the actual minimum. So minimum over both w and b of the Lagrangian will be equal to just this first part. So then we have this, we have minimized this over w. So the dual problem, what was left? It was left to maximize over alpha, such that all alphas are greater than 0 of this quantity. So this whole thing we have to maximize with respect to alpha. So one thing to note is that instead of working in earlier when we were working on with each data point. We were having condition with each data point. Here, instead of taking data points, we have xi transpose xj. That is, we have dot products of different points. Instead of taking xi, we need xi dot xj, xi dot xk. Like the sum runs over I1 to m. So we'll have m square dot products that we need as input to maximize this. Another thing to note is that in this problem, these conditions that we had, mm, these the Karush-Kuhn-Tucker conditions, these are already satisfied because we took this assumption in the beginning. Where is it? This gi less than equal to 0, we have taken as an assumption of the model. So that is the part of the KKT condition which we have satisfied, and the rest of the conditions, that alpha I greater than 0, that we have to take during maximization of this, and sum over alpha I yi equal to 0 is one condition which we have to take care of separately. So basically what we have is we have to maximize this quantity, keeping in mind that we have to maximize over all positive alphas, and we have to take this condition. So then the dual problems solution will be the same as the primary problem solution. So this seems like a lot of algebra, and we are doing a lot of things. Why we are doing this, that we'll come to that now. So first of all, we see what's feature mapping. So let's say we have a data like this. So if you have a data like this, it is not really possible to linearly separate it. No matter where we draw a line, there will always be some crosses to one side, some crosses to the other side, some dots to the one side, some dots to the other side. This will make it very like this is not doing the job what we need. So instead, what we want to do is, instead, let's say these are again axes x, let's say x1 and x2. These are the axes. So instead of taking x1 and x2 as input to the SVM, what we can do is take under root x1 square plus x2 square, which is equal to, let's say, r. This as an input to SVM. So what is r here? If we plot now, if we plot in terms of r now, so what we have is, let's say this is the 0 of r. So we'll have all the x is very close to 0, and we'll have all the circles very far from 0. So now it's very easy to linearly separate it. We just put a perpendicular line and we are able to separate it. So what this implies is, with some data, is it's easier to separate it if we move to a different coordinate system. In this case, this was a simplification because we moved from 2 dimension to 1 dimension, but in general, it's much more beneficial to move to a higher dimensional system. So with more dimensions, we'll have more regions to separate it, and that will help us in doing the SVM better on that. So still, we still haven't explained why we need the dual problem. So I'll come to that now. So what we have in the original problem is, let's say we have data points x, y, z. let's say there are three data points. They have some dimension. They are n tuples, let's say. So we have x, y, z, and then we use that to solve the SVM. But we just now saw that in some cases it's not possible. So these type of transformations, we denote them by phi. So instead of taking x, we move from x to phi x. So instead of solving for x, y, z, we want to solve for phi x, phi y, and phi z. But the problem that occurs here is this is sometimes computationally very difficult because each of these x, y, and z are n tuples, and these phi's are not necessarily n tuples. These phi's can be more. They generally are more dimensions than what we originally started with. So if these are n tuples, these can be n square tuples and cube tuples, and then computing it for each data point will be very computationally costly. So this is where the dual problem comes in. We saw that solving this xyz, instead of that, taking the dot product x transpose y, y transpose z, x transpose z, like taking these dot products is similar. We solve the same problem by taking the dot product. This holds true when we change the coordinate to phi as well. So solving this is same as solving phi x transpose phi y, phi y transpose phi z. Using these, the dual problem, if we solve, that we'll get the same solution as what we get in this one. So, but the thing is, since it's computationally we already said it's computationally costly to go from here to here. Going from here to here and then to here, that is even more computationally costly. So, what kernel does is that finds a shortcut way to go directly from here to here. Going from this to the dot product is just if there are n tuples, then it's not as costly as calculating n square or n cube tuples. And first of all, going from n to n square also. So we directly go from there to the dot product, and from dot product we can just transform them to this. Then this will, if we are able to do this, then that will be just the most ideal case. That is where kernel comes. The kernels comes in. What that does is instead of going all the way around, we do k of x z, uh, let's say two data points, and what we get is phi x transpose phi z. So we go directly from here to here or here to here based on whatever notation you want to follow, because a function of x and y will also be a function of the dot products and so on. So we go directly from there to there, and this makes it computationally more viable. How we can check using an example. Let's see. For example, let's say x and z are n tuples, and we define a kernel k of xz is equal to x transpose z whole square. So here we say we have the sum running from 1, 2, 3, 4 to n. We open up this x transpose z. What we get is xi zi, and since it's squared, we also multiply it as xj zj. So this takes this form at the end. So one thing you notice, this is a sum which has n square terms. The indices go from, it starts from 1, I, j is equal to 1, I is equal to 1, then I is equal to 1, j is equal to 2, then I is equal to 1, j is equal to 3, and so on. Then I2, j1. So basically there are n square terms in this, and each term is of the form x. Let's say if we check 1 and 2 term, it will be x1, x2 multiplied by z1, z2. This has the form of a dot product in some ways, because we are like the second entry, or if we form an x, this products of x and all the x1, x2, this will be x1, x3. It's multiplying with the that same index of the second data point, that is z. So which then we can argue that this kernel is actually this feature being dot product, like we're doing the dot product of this feature. So what we have is x1, x2, x1, 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 x2, x1, x3, so on till x1, xn. Then from 2, 1 to 2n, then 3, 1 to 3n, so on till n, which we'll have. So this is an n square dimensional feature vector. So, and this kernel is calculating x z transpose, sorry, phi z transpose phi x. So what we have here is this kernel is calculating the dot product of such a large feature, which just going from x to phi x would take us order of n square time, but finding this k just takes order of n time. So it's linear in the dimension of the input attributes. So this is how we see that using kernels we can save a lot of computational time. Here is where the dual comes into play, because if we didn't have the dual formalism, this dot product would have been useless for us. This dot product doesn't do anything. We would have to use this whole feature again. But because we have that the solution of the dual problem is the same as the solution of the primal problem, this dot products become useful for us. We can solve using this dot product the maximization of the Lagrangian, and then the solution we get there is the same as that if we had used these features there. So that's why we get a low computational time as well as a better classifier than if we had used just the simple SVM. So for the next part of the talk, my partner Adarsh will take over from here. Thank you.
Okay, so now coming over to some common example kernels that I use in SVM. We have polynomial kernels. The equation for this is given by k x1 comma x2 equals x1 transpose x2 plus c whole to the power d. Here x and y are vectors of features and c is a parameter which influences the weight of higher versus low order terms. When we keep c to 0, the kernel is called homogeneous. Generally, we keep the value of c to be 1. Now, an intuitive way to think is that this kernel looks at not only the given features but also combinations of them. Coming to an example, if we have a two-dimensional space and we have 2 points, say xa equals a1 comma a2 and xp equals b1 comma b2. Now say we want to map this to a 6-dimensional Z space. Then to solve this dual SVM, what we'll need is there are 2 methods. One is ZA equals phi xa. This is our transform. We'll have 1 comma a1 comma a2 comma a1 square comma a2 square and the cross term a1 a2. Similarly, we'll have zb equals phi xb equals 1 comma b1 comma b2 and so on. Then solving the dual SVM, we'll have ZA transpose ZB which will be 1 plus A1 B1 plus A2 B2 plus A1 square B1 square plus A2 square B2 square plus the cross term A1 B1 A2 B2. Now another method to solve this will be using a polynomial kernel, which is ZA transpose ZD equals K XA XB, which from the above formula is given by 1 plus XA transpose XB square. Here we're using the quadratic form of the polynomial kernel, and we see that we'll get the same terms as in the above equation. Thus, we can easily calculate the dot product by increasing the value of degree of kernel. Now, an intuitive example to understand this is, imagine we have the following one-dimensional data. This is our origin, and I'm using circles to denote one kind of data and crosses to denote another kind of data. And this is our x-axis. Now, if I apply a transformation, y equals f of x equals x square, then I'll transform this one-dimensional data into a 2D data set, and I'll get the following distribution, which looks like a parabola, which is a parabola. And I have mapped the data from the 1D to the 2D. And now we can see that it's very easy to draw a hyperplane separating the two different kinds of data set, which would have been very hard if we were doing it in the 1D data set. Because if we drew a hyperplane on the left side, we will have more than 50% error. If we drew it on the right side, it would still be more than 50% error. And if we do it in the middle, it will be exactly 50% error. Now coming to the applications, this kernel is used in image processing and natural language processing. One of the examples will be speech segmentation. So you have a spoken sentence which comprises of words, interruptions in between, silences, and noise. So here we can use polynomial kernel to distinguish between when something is being spoken, a word, and when nothing is being spoken. Our second kind of kernel is called Gaussian radial basis function kernel, RBF. This equation is given by k x1 comma x2 equals exponential minus gamma and the norm x1 minus x2 squared. An equivalent definition involves the parameter gamma, where gamma equals 1 by 2 sigma square, and we get the following equation. So this kernel, the intuitive way to understand would be, given 2 points, it computes how close or far they are to each other, and depending on that, it assigns a similarity to it. So if 2 points, the distance between 2 points equals 0, then the kernel function will give value 1, which it indicates that they are the same points. If the kernel function is close to 1 but less than 1, then that would indicate that these points are extremely similar. When these points are separated by a large distance, then the kernel value is less than 1 and close to 0, which means the points are dissimilar. And hence, this kernel helps us to compute the similarity between related points. Sigma here is our variance term and our hyperparameter. Now, as the value of sigma decreases, this kernel model overfits the data. And vice versa, if sigma increases, then the model underfits the data. This can be seen from these examples. Say sigma is 0.1, then our kernel function will be exponential minus d12 square by 0.01. The graph will look something like this. So we can see that the k value goes to 0 for x larger than 0.2. Now if sigma equals 1, then our k function looks like this. And the graph would look something like this. Here we can see k goes to 0 for x value more than 4. Now sigma is 10, and for the corresponding k equation, you see we get a very broad valued graph. Here we are literally getting all the values to be same, so we are underfitting the data here. K goes to 0 for a value of x more than 10. So we need to adjust the sigma value, so we need to tune it. To get the best fit. Coming to applications. It is similar to the k nearest neighbor algorithm, KNN. overcomes the disadvantage that KNN has, wherein it needs to store the support vectors during training. And doesn't need the entire dataset. Examples of a few other kernels. We have Sigmoid kernel, whose equation is given by kx1, x2 equals tan hyperbolic alpha x1 transpose x2 plus c. This is used in neural networks as an activation function. It is similar to a two-layer perceptron model of neural networks. Next we have a cosine similarity kernel. This function is given by kx1, x2 equals x1 transpose x2 by the norm of x1 and norm of x2. This is a popular choice when it comes to finding similarity in text documents. Which is like a plagiarism check. The L2 norm projects the vectors onto a unit sphere and the dot product is the cosine angle between the vectors. There are a lot more kernels which are popular, such as the Bessel function of first kind, which is used to remove the cross terms from mathematical operations, and the ANOVA radial basis kernel. But these are a bit outside the purview of this lecture. Thank you.